Welcome to our presentation about direct hydrocarbon indicator analysis that is available within Paradigm 14 for every interpreter. Within the last few decades, we have seen major improvements in reflection seismic acquisition, processing, and interpretation methods that have enabled us to interpret the presence of hydrocarbons directly from seismic data, not only using traditional qualitative interpretation methods, but also using quantitative techniques. Let's have a look what is a direct hydrocarbon indicator. So a DHI is a seismic measurement that suggests the presence of hydrocarbon accumulation. This technology first started with bright spot analysis, where some anomalously strong bright amplitude reflections on the seismic sections were associated with gas-filled sands. Nowadays, it is a more general term, direct hydrocarbon indicator, or DHI, and it includes bright spots, dim spots, flat spots, phase change, and even amplitude variation with offset, AVO. The ultimate objective is to accurately predict the geological conditions that have caused these characteristic geophysical responses, and it is also possible to predict the presence, the thickness, and lateral limits of potential hydrocarbon areas in the reservoir. Unfortunately, what appears to be a typical seismic response from a hydrocarbon accumulation is sometimes caused by something completely different, and geophysicists who have experienced these unfortunate results have had reason to label DHIs as a dry hole indicator. So, to separate this false DHI from the true DHI and correctly predict the actual geological conditions that has caused this true DHI, some of the most difficult tasks that geophysicists are facing today. We also know that the pre-stack seismic data carries critical information related to rock properties and can influence structural interpretation and lithology predictions. Fortunately, with Paradigm, we have access to pre-stack data that now are available to every interpreter through the support of simultaneous display and interpretation of pre-stack and post-stack data in a shared 3D visualization environment. So in this presentation, we will be able to see the value of powerful quantitative seismic interpretation and characterization workflows, so we can avoid dry holes and minimize our drilling risks with the access to Paradigm quantitative seismic interpretation workflow. The study area we are going to be focusing on today is located in Taranaki Basin, and it is quite well studied and a lot of knowledge accumulated after years of exploration. The sand reservoirs are well mapped, but now the challenge is to analyze deeper reservoirs around mid-Miocene horizon. First of all, we're going to look through the AVO workflow that will enable us to generate hydrocarbon prospect areas. Thanks to our new Gather Conditional tool, we will be able to QC our input data quickly and efficiently. Once our data is ready, we will generate angle stacks, and we also perform the AVO attribute generation and prospect zones generation, so we can validate our prospect zones with the pre-stack data and generate our maps of the prospect zones. As we know, one of the most important steps through the AVO workflow is to perform AVO analysis on the well data. So we've done the AVO synthetic with the gas substituted log, so we've performed the fluid substitution, and you can see that the synthetic AVO response is typical for AVO class 2 anomalies. So we will remember this fact and we will use it later on in our workflow. And now we're gonna switch to our live demo. So here in 3D visualization tool, we visualize two horizons. The top one is mid-Miocene and the bottom one is Eocene. These horizons were interpreted using the post-stack data, and our aim is to use pre-stack data so we can identify our prospect reservoir zones. So let's open our pre-stack data first. So here we can see our pre-stack data, so let's remove our amplitude volume, and we can also restrict our horizons. As you can see, the data looks very noisy, and they also, if we zoom in, we can see that the reflections are not flat, so it makes our data very difficult to use to evaluate our AVO anomalies and DHIs. In Paradigm 14, interpreters can now perform gather conditioning and inversion operations directly in 3D canvas. This allows you to easily incorporate rock property and AVO analysis in your interpretation workflows, all within the single application. So let's have a look what we can do with this data. So first of all, let's analyze the frequency range of the seismic data, so we can apply the filter to remove this noise. So let's estimate our frequency range. So we're using our seismic spectrum analysis tool, and the seismic spectrum tells us that we have a problem with the high frequency noise here. So to remove this high frequency noise, we're going to use our pre-stack processing tool, and we can apply the bandpass filter to remove this high frequency noise. So let's have a look at our gather conditioning tool. So this is where we can select our bandpass filter. So we would need to set up our high frequency filter, and we can easily apply. So as you can see, the data is automatically displayed in 3D viewer. And we can switch before and after. So also we can see the effect of our bandpass filter, and as you can see, we've removed this high frequency noise, and the gathers became much more clearer. So we removed all this high frequency noise from the data. So also we've noticed that the data doesn't look very flat. So the main target events within the data are not flat, and this is not very good if we're going to use our AVO analysis tool. So for this purpose, we first need to flatten our gathers. So in our preconditioning tool, we have several ways so we can flatten the gathers. So first of all, we can use the automatic NMR correction. It is based on AVO approach and for residual move-out analysis. Or we can output residual move-out from this auto NMR correction and smooth it and then apply it on the fly to in our NMR RMR correction mode. So we can use existing residual move-outs or velocities from other applications. So in this demonstration, we're going to use this last approach. So we need to set up all the input data. So first of all, the velocity file that we're going to be used, and then also the residual move-out velocities, and in this case it is a second order correction. And we can apply to our data. This will only run on the displayed line, and the results are stored in memory only. So this means that we can change all the parameters easily and run the process again to find the best filter for the data, and then the resulted data is displayed in our 3D viewer tool automatically. As you can see, we can switch between the unflattened data and flattened data very easily. Also, because we are working in a 3D environment and a 3D visualization tool, we have the option of visualizing these two datasets together by merging this data. So in our case, we're going to be merging these two datasets. So basically the dataset with the noise removal, and then also the dataset when we flattened our gathers. So we can also use the different merged methods. So in our case, we're going to use the subtraction just to show us what is the difference between these two datasets. And we can see that the biggest difference is between our mid offsets and the far offsets. So if we scroll through the data in our CDP domain, and you can see that the biggest difference again between our mid offsets and the far offsets. And this is why flattening our gathers is really crucial for our further AV analysis and angle stack calculation, as if we didn't flatten the gathers, obviously our angle stacks, especially the mid and the far, would be not correct. So another way of looking at the data is displaying them in our conventional 2D viewer. So let's open our gathers in our 2D viewer, in a 2D canvas. As you can see, here we're displaying simultaneously our original gathers, so the noise gathers, and we can move them interactively to our left side. And then also we're displaying our preconditioned data, so the data where we applied our first bandpass filter to remove the high frequency noise, and then also we've applied the NMR correction. As you can see, we've significantly improved the data quality. The data looks much more flattened. And so now we are ready to investigate our AVO potential. So the AVO plot tool will track the amplitudes along the target event. For us, in our case, it's just around this area, and you can see what's the typical behavior of our amplitudes. So the dashed line will represent the second and third term approximations of the Sopritz equation. So here we are looking at the data, the amplitudes that we've taken from the raw data, from our regional data, and now let's have a look at the same event but on our preconditioned data. As you can see, the amplitude behavior is quite similar. The only difference is that we've actually flattened the gather so that we have a much more correct way of estimating the angle stacks and the AVO attributes. And you can also see that the amplitudes are behavior corresponding to AVO class 2 anomaly. So, and we also remember that from the AVO well data analysis we've established, so with the gas filled reservoir we have the AVO class 2 anomaly. So we can see that we definitely have a potential in our area in this survey. So also from this amplitude behavior we can judge that the hydrocarbon effect is mostly in the far set data, so it must be useful to create near and far angle stacks, so to compare our near and far event amplitudes to find anomalies that could be due to hydrocarbon presence. So next step would be to generate our angle stacks, and it would be nice to have an idea of what is the angle range for this data within our target interval. And so we're going to launch our gather conditioning tool again, and there are two ways to get this information. First of all, we can use the offset angles conversion to generate angle gathers from our distance gathers, or alternatively we can use the incident angles operation on the corrected gather, so to create the incident angles attribute. So we're going to use this last option, and we're going to switch to interactive workflow builder. This is where we can build our workflow interactively. In our case, we're going to be using our corrected flattened gathers that we have now displayed in our 3D viewer, and we're going to select incident angles operation and apply. So both of these operations are using the global velocity that we have defined in the global parameters tab to convert offsets to angles. So now, for easily a view of this dataset, we can merge this data with our flattened gathers. So in our case, we're going to be merging our incidence of angles with the corrected flattened gathers, as you can see here, and we would just need to interactively change the histogram of our angles of incidence, so we can have an idea of what is the range for our dataset. So as we can see, the angles of incidence are varying between 0 and about 30 to 35 degrees. Now that we know the angle range for the gathers, we can use the AVO inversion operation to generate our angle stacks. So in this case, we're going to go back to our gather conditioning tool again, and we're going to select our flattened gathers, and we can select the AVO inversion operation. This is where we can define our parameters for the calculation, such as the inversion type, 2 parameter, 3 parameter, also some different average window, significance level, etc. Also, this tool will allow us to calculate the standard AVO attributes such as normal, incidence, reflectivity, or gradient. But in our case, we're going to be working on the angle stack calculation, and let's calculate just these two angle stacks between 0 and 10 and 20 and 30. Okay, and this operation will be applied to our flattened gather line that we've just displayed here in our 3D viewing tool. So once everything is calculated, we can display it in our 3D viewer. So now it is not a pre-stack data anymore, it's a stack data. So we're gonna switch to our amplitude display. So we can switch off our pre-stack data. So this is one of the angle stacks that we've calculated. So let's check. What is this? So this is the 20 to 30, and we can also view the 0 to 10 degrees. So what is the best option to interpret this data set? Obviously the most easiest would be to cross-plot this data. So to really focus on our target, we need to limit the cross-plot to the region where we're interested in. So we are going to use our horizons as a limits for the cross-plot. So we're going to set up the mid-Miocene horizon as the top horizon, and we're going to put 0 milliseconds as the offset above, and then the Eocene horizon we're going to use as the bottom horizon, and again 0 milliseconds below. And then we just need to select our angle stacks that we're going to cross-plot and cross-plot them together. So here we are going to see our cross-plot. So the idea is to define a trend line, and then we're going to color it relevantly to the distance from this line. We can also send this data to the seismic cross sections that we are displaying in the 3D viewer. So we're going to adjust the color scheme for the cross plot. So the idea is to look for the data that will be furthest away from the trend line. So that would be our AVO anomalies, and they are displayed in this pink color. Okay, so we can see all these anomalies just along the top of this horizon. So here we are displaying this data only on a 2D section, on one of the inline displayed. So we can take this information and we can create a 3D volume, and we can display it here in our 3D canvas. And we're going to also use the opacity. So we're going to isolate all these values that are represented by the pink color, the furthest away from the trend line. So this is where the areas will be associated with our AVO class 2 anomalies. So we're going to apply the opacity, and as you can see, all these areas stands out from our volume quite nicely. So these are the areas with the potential AVO class 2 anomalies, and we can take this information to our voxel-based analysis tool, VoxelGeo, and detect these areas that will represent our prospective DHI AVO class 2 anomalies. Okay, so here we can see these are the potential geobodies that are associated with the AVO class 2 anomalies. So we have generated these geobodies, but how good they are. So we want to validate our results against the pre-stack data. So let's pick our pre-stack data. So we're going to open an inline of gathers, and let's pick somewhere around this area. So the data will be loaded into 3D viewer automatically. Alright, so we just need to adjust the color scheme of the data. And we can also adjust the position of the C2P to somewhere around this area, so we can clearly see our generated geobody and the seismic gathers. So now we're going to use the 3D propagator to analyze this prospective area. So let's restrict this horizon, and I'm going to launch the 3D propagator. So we're going to use the inline that we've just loaded, and we're going to propagate one of the geobody, which is the send angles 1. Let's define the event type, which is a red, corresponds to the minimum. And then we're also going to use the post-stack peaks as the external seeds for the pre-stack propagation. And let's put a seed on our gather somewhere around this area, and let's run. So if I unrestrict, as you can see, it did propagate quite nicely through the data. We can also display the amplitudes that were extracted during the propagation process, and we can just adjust the color scheme again. And as you can see, we have a clear indication of the AVO class 2 anomaly, as we can see that negative values are increasing with offset when we go towards the far offset, so the negative value is increasing. So that's definitely around the AVO class 2 anomaly. So that conforms with our initial guess. So in this way we can validate and verify most of our geobodies that we've just generated. So let me put them back on our display. So now to have a true direct hydrocarbon indicator analysis, we would need to bring our seismic inversion to our workflow, and for this we're going to switch to the PowerPoint slide for a second. So now when we've completed our AVO part of the workflow, we can continue it and perform the inversion for our rock type and fluid characterization. So again, first of all, we would need to control the quality of the seismic, and we would need to calibrate our wells to the seismic data. Also, it is very advisable to run feasibility tests of inversion with rock physics, and then we would need to build a low frequency background model and perform our pre-stack maximum likelihood inversion. And then once it's done, we can interpret and analyze the inversion attributes. So let's switch to the live part of our demo again, where we can go through different steps of the inversion workflow. So first we're gonna need to analyze our well data, as it provides a clear definition of where we could find clear sand pay zone. Here we're gonna generate a cross plot between the two well properties, P impedance and Poisson ratio, that we've displayed in the first two columns of the well template. So this well goes through the target area. We're also displaying a gamma ray log here, and density and neutron. So we've cross-plotted this P impedance and Poisson ratio logs, and we also color-coded it by gamma ray logs. As you can see, on this cross plot, the red color represents the sand areas, and the blue color represents the shale areas. So first we would need to define a shale line, a shale trend, and then we can color our cross plot data relevant to the distance from this shale line, and we can simply send this information back to our well log display. And as you can see, the P impedance and Poisson ratio crossplot gives us a very clear separation between the sand and the shale areas. So through the petrophysical analysis, we can separate different lithologies in the P impedance Poisson ratio domain. So what we need to generate is our seismic P impedance and Poisson ratio volumes, and for this we're going to use our pre-stack inversion method, which is in paradigm 14, is accessible from the gather conditioning tool. So let's go back to our 3D viewer and launch our pre-stack conditioning tool. So here we are displaying our line of gathers, as we are going to run the pre-stack inversion, so we would need our pre-stack data. So here we are displaying just one line, as a test line. So we've selected the pre-stack maximum likelihood inversion from the list of operations. As the input data, we would need to define our background model for the P and S impedances. Also, you can define the background density. Also, we would need to define obviously the wavelet, the amplitude calibration factor, the background model weight, which is one of the constraints on this inversion, and then also another constraint would be the deviation from the background model. As the additional outputs, this inversion can produce synthetic gathers, residual gathers, also the VP-VS ratio and Poisson ratio. So in our case, we would just calculate the P impedance and the Poisson ratio. So let's have a look at the results of the inversion. So here I'm displaying the P impedance and Poisson ratio that we've calculated from the pre-stack inversion method. So the best way would be to cross-plot these two volumes together, and this is what I've already done. And here I'm displaying the result of the cross-plot, color-coded by the trend line and the distance from this trend line that we've achieved from the well log cross-plot. So here pink color would represent the sand areas, and then the green and blue would represent the shaly areas. So here the idea is to isolate all the areas that would be represented by the red and pink colors, and for this we mainly can use the opacity tool. Right, and so this is just a 2D display. So the idea would be to create a cross-plot in 3D and isolate these areas. So again, we can take this information, the full 3D volume of the crossplots between P impedance and Poisson ratio, to our voxel-based analysis tool and detect all these bodies that would represent the pink color using our subvolume detection technique. So let's bring these bodies to our display. So here we have the resulted bodies from the inversion, and then here we can display the resulted bodies from our AVO anomalies that would correspond to our AVO class 2. So the best way to look at this data would be to open this up in our basemap window. Okay, so in this basemap view we are displaying the structural map for the top horizon of the target area. So we're going to display the polygon that would correspond to our bodies detected from the AVO analysis that would correspond to our AVO class 2 anomalies. So this is the whole area. And then also we can display on top of it all the bodies that were detected from the crossplot of seismic inversion, Poisson ratio and P impedance results. And as you can see, these areas, they intersect, and for us the most probable chances would be to find the true DHI that would correspond to our sandy reservoirs with the AVO class 2 anomalies, would be where these two polygons intersect. So for us, this would be our final zones where we could potentially try to place a new well. So for example like this, so we can potentially, based on our structural information, we can place a well like this. So we've completed our workflow where we've performed the AVO analysis to detect the potential hydrocarbon areas that would correspond to AVO class 2, and also we've performed the inversion workflow where we were able to detect the areas based on the sand and shale zone separation, and then finally we were able to position our new well in the most probable and best area within our survey. So to summarize our presentation, I would like to point out a few key points. So first of all, we were able to perform our gather conditioning simultaneously in a shared 3D visualization environment. We were also able to identify prospect hydrocarbon zones, its lateral limits with easy access to AVO and pre-stack inversion tools, and also we were able to avoid our drilling hazards and minimize the drilling risks by validating our potential prospect zones against the pre-stack data. Thank you for your attention, and you're welcome to any questions that you might have. Please forward them to me. Thank you.